Interesting problem. Basically outlines a one current carrying wire and then a square loop of wire near that current carrying wire, and it asks us to find what is the magnitude of the induced EMF in that square loop of wire. So I drew the situation right here. This is just, there's part 1 and part 2, so this is part 1. We know that there's a wire like this with current going up through it, and then we have this square loop with side lengths L and L, and then a distance D away from the current carrying wire. So we know that the EMF, which we're trying to find, is the change in the magnetic flux over the change in time. So we can actually just calculate the magnetic flux of this little strip dr, which is just equal to dB dA, and we know that dB, magnetic field of a wire, so at some point in this little strip here, is going to be mu naught times I, which is current, and over 2 pi d. So this kind of looks like an F. It's supposed to be I. But remember that this distance, d plus whatever this little distance portion of L is, that the magnetic field is going to be the same for this whole dr. But as soon as you go to the side, it's going to be different. The side's going to be different. So later on, we're going to have to take an integral to find the sum of all the different magnetic field strengths in this whole box. So we can substitute for this. It's phi. Yeah, definitely phi. Instead I pronounced phi or phi. So now we can integrate. Once you have the expression for the change in phi or phi. So you go from d to d plus L, because this is the distance d from the wire and this is the distance d plus L. So you want to integrate this strip from here to here. So actually, because we're only integrating with respect to r, most of these things are just constants. Mu naught over 2 pi is obviously just a constant, and I and L can be treated as constants. So you can remove mu naught and I and L over 2 pi from the derivative, so you just get 1 over r, which is obviously just log r. And because this is natural log, between the d plus L and over d, or between d plus L and L, instead of having to do this d plus L minus this and d, you can just say, you can just write it like this. So the flux is equal to mu naught IL over 2 pi natural log of d plus L over d, which is really nice because that's way easier to write it like that. So now that we had that expression on the previous page, we can substitute in the problem. It gives us what I is equal to as a function of time. So we actually learned about it a few weeks ago in class, but it's or this type of expression. But I of t, so the current as a function of time, is equal to I naught times e to the negative t over RC, because it's an RC circuit. So we can just plug this into here, and then for this value of I, so we have phi is equal to, or phi is equal to mu naught I naught e to the negative t over RC times L over 2 pi, and then our natural log of t plus L over d. Actually, I just realized this could just be 1 plus L over d, but that doesn't matter because this is just d over d. So we're almost done, and we know that E, which is the EMF, is just equal to d phi over dt. So we need to take the derivative to find that. So because we're differentiating with respect to time, because it's over dt, most of this expression doesn't have time in it. So again, we can just make it easy on ourselves and pull out the things that don't have time. So that's how I wrote it, is mu naught I naught e to the negative t over RCL over 2 pi natural log of d plus L over d dt is just equal to all of this out front, and then basically e to the negative t over RC dt. So taking the derivative of this is pretty easy because we just know that the derivative of e to the thing is just e to the thing times thing prime. So you can have this expression very similarly written, except with the derivative taken of this portion with t. So yeah, so I said this is the only term that has t in it, because this is the only term that actually involves time. So when you take the derivative, you can just say it's the EMF of that square loop of wire is just equal to mu naught L times 2 pi natural log d, that distance away, times, plus L over d times the initial current I naught over RC e to the negative t over RC. So this is kind of a messy way of writing it. There might be a cleaner way of writing this, but it's the expression for the EMF. So part 2, interesting. Part 2 asks, will this loop of wire be pushed towards or pulled away from? So I said that the magnetic field that it will be experiencing by this current carrying wire is into the page, and we just know that from the right-hand rule, and it's going to be decreasing. So that makes the induced field be into the page, because if it's into the page and decreasing, the current carrying wire will say, no, we need to keep it into the page, so it's going to go back. It's going to induce a field that's into the page, so it doesn't, to counteract the change. So the induced current, using the right-hand rule again, will be clockwise. So the current will be going around like this, and we know from chapter 32 about magnetism and current carrying wires that two parallel wires will exert a force towards each other if the current is going in the same direction. And here we can see that yes, indeed, the current is going in the same direction, so they will exert a force. They will attract each other, basically. So, and this wire is actually also parallel to this wire and going the other way, but because this distance is so far away, I'm sure it'll have some effect, but it'll be pretty negligible because it's so far. And this wire will really be pulled towards this current carrying wire. I guess this wire is also carrying current, but this main wire. So it'll this loop will be pulled towards the straight wire.